This meeting is being recorded.
This video is going to be a continuation of section 7.8, and we'll begin here with a review of rearrangements. So whenever we have a carbocation that is generated, such as with SN1 and E1 mechanisms, a carbocation, if possible, may rearrange through a 1,2 hydride or a 1,2 methide shift. And what this means is that a methyl group or a hydrogen may move its position to generate a more stable carbocation. So the general rule is that when a carbocation rearrangement is possible, it will occur. So always be on the lookout for more stable carbocation arrangements than when an initial leaving group occurs. So for example, we have our leaving group here, and we would generate a carbocation at this site here. So what we see is if a 1,2 hydride shift occurs, so we have a hydrogen here, then hydrogen can shift over to where that carbocation was, and then our second product can be generated here. So now our carbocation would be here at this tertiary site, rather than previously it would be at a secondary site. So we can generate different products before and after a 1,2 hydride shift, or down below here, if our carbocation was generated at this site here, one of these methyl groups can shift over here first, and that's what we see here. And then this second product can be produced after a 1,2 methide shift. So of course, with either solvolysis or in general SN1 and E1 reactions, we're going to have a mix of substitution and possible elimination products. So again, let's take a look at some substrates and discuss whether or not rearrangements would be possible or if they're common. So when we have a primary substrate and it's reacted under those solvolysis conditions mentioned previously, such as things like ethanol acting as a solvent or water, which also causes this reaction mechanism to be initiated. In this case, we have water here. We'll see this leaving group, this bromine, and we would generate a primary carbocation, but we note here that this product, this primary alcohol, would not even be observed. We would only see the substitution product of our more stable carbocation, and we would actually see this process as a concerted process. So this methide shift, so that's what we see here, this methyl group being shifted to generate this more stable tertiary carbocation, and that's where water will act as perform this nucleophilic attack, and then once again we have that subsequent proton transfer to create our alcohol product. So again, if a carbocation rearrangement can occur, it generally will occur. So we can also discuss some of the effects of solvents in this section here. So we should note that SN1 and E1 reactions will react faster in a protic solvent. So we can take a look at either protic solvents, so things like alcohols that have an OH in them, or we have polar aprotic solvents, so things that do not have a hydrogen bonding type of proton, or very different electronegativity, very polar bond, so something like an OH bond. But in these aprotic solvents, these reactions are slower, and we see this increase in rate, or rather are faster rather in these aprotic solvents than these polar protic solvents rather. So let's take a look at why this is the case. So for SN2 reactions, a polar aprotic solvent we say is best. Aprotic solvents will raise the energy of the nucleophile, and this therefore lowers the activation energy required when we have a polar aprotic solvent. So this is good for SN2 reactions, but when we have SN1 reactions, we see the opposite with a polar protic solvent. These are able to stabilize our carbocation intermediates, which would then lower the activation energy and make SN1 reactions faster. So again, we see that down here, polar protic increases the rate of SN1. So remember SN2, polar aprotic, SN1, polar protic would increase the rate. So what about the substrate? What differences can we see based on our substrate and the reaction rate? So here we're told that the better the leaving group, the faster the SN1 or E1 reaction. And that's because we need to generate that carbocation and a halide ion. So the more stable the halide ion, the faster the rate of ionization. So we can see that smaller fluorine turning into a fluoride ion would be the least reactive, then the larger iodine, which is able to be a more stable halide ion. So we can also look at the substrate intermediate stability. So we know that a tertiary carbocation is stable enough that we can see a solvolysis process occur at what we refer to as a practical rate. We can also see that with benzoic carbocations or allylic. Both of these last two are resonance stabilized. So overall, all of these are stable enough that they would run this type of reaction fairly quickly, right? But we know that primary and secondary alkyl halides are going to be too slow for any use in this type of reaction. So we should be able to judge whether or not a certain alkyl halide will undergo solvolysis. So again, we can say that primary or secondary would only undergo this type of reaction if a rearrangement is possible to generate a more stable carbocation. So things like a primary to tertiary or secondary to tertiary could definitely occur. And then if we have a tertiary to start, allylic or benzoic alkyl halide, so any of those three carbocations being stable enough without rearrangement could also produce a mixture of SN1 and E1 products. So that's what we see here. This benzoic substrate would produce a carbocation here, and then we see an alcohol with substitution and our elimination E1 product here. So we should also consider, just like with E2 reactions, E1 reactions also can have multiple sites of double bond formation. So we can have multiple elimination products as seen with this substrate here. So once again, we would pick our alpha carbon, look for different beta carbons. These two are the same. And then we have a beta carbon here, both of which have protons that could be deprotonated, that could be removed. So if we were to remove a proton over here, we would generate this first product. If we were to remove one over here, we would generate this second product. And we would always give the most stable alkene as our major product. So that would be the most substituted. So this here would be our major product. But we can have these regioselective reactions, but we cannot control the regio selectivity in an E2 reaction. So that's good to note, that these can be regioselective and we can control that, unlike with E2 reactions. We should also consider the stereochemistry and stereoselectivity of reactions. So depending on our different possible stereoisomers that can exist. So we would have this leaving group and generation of a carbocation. Here we can have our major elimination products seen here. This would be our Zaitsev, that is the most stable, the most highly substituted alkene. Then we have our Hoffman over here. So we have, again, this would be our major product for this elimination. And then we also have our substitution product shown. When we have two stereoisomers that are obtained, we should note that the least sterically hindered isomer would be considered our more stable isomer. And we noted prior that these are stereoselective reactions, but a mixture of all of these products will still be obtained, even though we call it stereoselective. So speaking of stereoselectivity, these last two slides will comment on that. We're going to generate two products, and we will have a slight preference for inversion of configuration if we have a chiral center, because what we see here is after loss of this leaving group, our nucleophile is more likely to attack from the back side than the front side. Very slightly more so that we see a slight inversion of configuration. So again, even though a mixture of configuration is obtained, we generally say that there's slightly more inversion of product than there is retention of product. And we're shown here why this nucleophilic attack is hindered. So this would cause an inversion of product over here. I'm sorry, it's unhindered rather. So this is our greater percent, and then we have it hindered over here. So we would see slightly less product. So we will continue with the next section in the next video.